would need to look at it. I will post it because I sent you guys an email actually a few minutes ago, maybe an hour ago. Because now I'm going to be posting a bunch more videos because I'll be doing one every time somebody's absent. I did create like a separate playlist for IB physics versus this class. So that will start getting pretty clogged up there. All right, so last time we did talk about Kepler's first laws. We talked about some of the, if that's right in your way, sorry, it will. We talked about some of the people leading up to Kepler, and we said that Kepler did have all this great data that was collected by Brahe, and he was able to come up with these 3 laws of planetary motion. Right? Newton, decades later, came up with 3 laws of just regular, generic motion. All right? So Kepler's first law, we said, addressed the shapes that the planets make as they orbit the sun, and he said that the shapes were ellipses, right? Not perfect circles. Most of the planets have very near circular orbits, right? Mercury does not, and most of the other things in our solar system don't either. Ruchi Groundsheet, can I help?
Oh no, I just had a question.
Okay. Now, Kepler's second law, it actually is quantitative, but we're probably not going to look at the quantitative nature of it until kind of the end of class today, or possibly even on Tuesday. So I'm gonna give it to you, but then we're going to take a step back and remove some of the complexity from it for at least our purposes right now. So an imaginary line, right, that connects the sun and whatever the heck planet we're talking about sweeps out equal areas in equal times as that planet goes around the sun. Right, again, we'll see that equal areas in equal times, right? Maybe that makes sense to you, maybe not. But for our purposes right now, right, as we just look at these 3 laws for the first time, this does tell us that when we're closer to the sun, we move faster, and when we're slower from the sun, we move, when we're further from the sun, we move slower. So let's take a look at that before we move on to the third law. Do we know the names of any, what do you call them, comets?
Haley.
How do we know that?
Haley's like a big one.
I know, but like, how do you know that? Like, you weren't born last time it came around.
Because
It's
like I was talking about
famous.
it.
It's just famous?
Yeah.
Yeah.
Isn't it like every 72 years?
It's like every 86 years,
It's
I think.
basically a lifetime.
Alright, so let's draw this. So here's the sun, alright? And then Halley's Comet, like just about everything that's not an asteroid or a planet, has a very eccentric orbit, not circular at all. Alright, so let me kind of draw. And in fact, I think we saw it last class. So this would be roughly the ellipse that makes up the orbit of Halley's Comet, and then here's our sun. The Earth might be something like, where would the Earth be? The Earth is probably like out here. No, the Earth would have a circular orbit. I'm not setting myself up for a circular orbit. Yeah, something like that. The dashed line might roughly be the Earth. I might even be off by like a factor of 10 or 20, but whatever, it doesn't matter. Now, Halley's Comet, I think, has a period of 86 years. The only reason I think I know that is that it last came in 1986, and I was like old enough to know about such things. So 86 years it takes for Halley's Comet to go around its orbit once. Really, I think it's the orbit is even more eccentric than I've given credit for. So let me just modify my drawing slightly. Alright, so back in 1986, I might be off about this a little bit, but I seem to remember people talking about Halley's Comet for like a couple of months. Like, there was a couple weeks ahead of time, they're like, hey, there's going to be this comet, make sure you buy your telescope. And there's a few weeks of, hey, you can see it tonight. Oh, you can't see it tonight because it's cloudy. You can see it like tomorrow night. So maybe we were able to see it for a month and a half. A month, something like that. And we'd really only be able to see it if it was pretty close to us. So maybe, because it's small, right? So it probably needs to be, within our orbit if we were going to see it. So that is like maybe 2 months tops that it takes Halley's Comet to go around this part of its orbit. And then it would be like 85 years and 10 months to go around the rest of the orbit. So for something like Halley's Comet that has a very, very, very eccentric orbit, this faster when closer to the sun, slower when further from the sun, can be very, very, very dramatic. Right? When it's way out here, it's going at a snail's pace. When it's here, it really just whips around, super, super fast. The Earth, with our very circular orbit, we have practically no difference in our orbital speed. close and none are far. Imperceptible difference. So anyway, we're going to come back to Kepler's second law, and we'll see it, and we'll talk about these equal areas and equal times. But follow-up issues right now about us saying that this does mean that when things are closer to the sun, they move faster, and when their orbit is further from the sun, they move slower. All right, yeah, there's really not much to belabor about that. Now, Kepler's third law is entirely quantitative, and it was the trickiest thing that Kepler came up with. And his third law relates the orbital period to the orbital radius for a given planet. Really, for two given planets. Alright, so I'll go ahead and write the Kepler's third law up here, but I want to just talk about one thing before we start addressing how we would use it. So again, this is relating the period of planets to their orbital radii. So let's take 10 seconds and see if you can answer, what is the period of the Earth's orbit? All right, let me not say anything else, but see, have an answer in mind. What is the period of the Earth's orbit? Raise your hand if you have some sort of answer. All right, not too many of you. So let's remind ourselves what the heck a period means. Period we first looked at with circular motion just a few classes ago. And we said that it's the special amount of time that it takes something to repeat its motion. And for things that are traveling in a circle, it's the special amount of time that it takes to go around the circle once, right? So let me give you another 10 seconds to think about it, right? How much time does it take the Earth to go around the sun once, right? Again, just get the answer in your head. I'm not looking for you to shout it out. All right, raise your hand if you have some sort of answer now. All right, that's quite a bit more of it. So what is it? 1 year. Yeah, well, 365 days, or 365 and a quarter days, or whatever. But 1 year, right? That the definition of 1 year is the amount of time it takes the Earth to go around its orbit once. Right. So when we're talking about orbital period, we're talking about how much time it takes the planet to orbit its star one time. When we're talking about orbital radius, we mean how the heck far the planet is from the sun. Right? That would be the radius of this circular, or at least near circular orbit. So Kepler's third law doesn't really allow us to calculate those things for a given planet, but it does allow us to relate the orbital period and orbital radius for one planet to the orbital period and orbital radius for another planet, right? Now there is one very important criterion that has to be met for us to use Kepler's third law. Our two objects, object A and object B, both do have to orbit the same thing. So if we're talking about planets, that's fine, right? Earth could be one object, Venus could be the other object, that's fine. What we couldn't do though is use Venus for object B and then the moon for object A. Kepler's third law would not allow us to do that because they don't both orbit the same thing. The moon orbits the Earth, Venus orbits the sun. So we do need to make sure that they're orbiting the same thing. Now, whenever possible, right, we want to make the Earth object B. And the main reason we want to make the Earth object B is that the period is 1 year. And it's pretty nice to have denominators of 1, especially when we're doing things like squaring or cubing, right? You don't have to do that. You don't have to make the Earth be object B, but it does just make the math a little bit cleaner. All right, let me show you an example of the type of problem that we would use this for, and then we'll see what questions we have, and you'll try at least one of these on your own. In fact, maybe I want to do 2 of these for you. All right, so Saturn is 9.3 times further away from the sun than the Earth is. How long is a year on Saturn? That's not a whole lot of information, but it's actually enough to be able to use Kepler's third law to find how long the year is on Saturn. So let's see, we're supposed to draw some sort of picture. What should I do? I guess I can draw the sun, I can show the Earth, and I can show Saturn. That's a picture, right? That qualifies as step 1. What's next? We're supposed to identify the information we know. There's not much here. I do know that I'm going to use the Earth as object B and Saturn as object A. That might be worth writing. I do know that the period of the Earth is 1 year. I know that I'm looking for the period of Saturn. I'm actually going to go ahead and do this right inside my equation. If we're talking about how long is a year, like we are definitely using Kepler's third law. There's nothing else we would consider using. So I'm just going to go ahead and actually start from my equation. So TA, if Saturn is object A, that's my unknown. TB, right, I'm making that 1 year. Go ahead and I'll leave the unit there, whatever. Now, I don't really know RA or RB, but I do know the ratio of RA to RB. All right, and let me write this down, but then I'm going to elaborate on this. The ratio of RA to RB is 9.3 to 1. Right, that's kind of covertly stated here. Saturn is 9.3 times further from the Sun than the Earth is. We could put values in. Right? In fact, astronomers are pretty smart. They invented a unit of astronomical distance called the astronomical unit. All right? And astronomical unit is defined as the mean distance between the Earth and the Sun. Don't write this down. Don't write this part down. So if we use that unit of measurement, RB is exactly 1 astronomical unit, and then Saturn is 9.3 times more than that. So that would be 9.3 astronomical units. Because I'm a science nerd, I know that Earth is 93 million miles away from the Sun. It's not SI units, but whatever. And then Saturn would be 9 times 93 million miles. I think you can see, if I divide this one by that one, I'm still going to end up with 9 to 1. So if you want to, put the actual distances in, be my guest, but we don't have to. Whatever unit of measurement we use, Saturn is going to be 9.3 times greater than Earth. So I'm just using that, right? That is the only difficult part of using Kepler's third law, is getting used to working in ratios. It's not really something we've tried to do yet. All right, so let's finish up with this, and then I'll see what follow-up questions we have. All right, so now I just have to do some algebra. So the numerator squared is just TA squared. 1 squared is just 1. I could get rid of the denominator of 1 and just call this 9.3 cubed. I suppose I can just get rid of this denominator of 1 also. So I've got TA squared equals 9.3 cubed. Have we seen cubes yet in this class? I don't think so. Let's make sure we know how to do that on our calculators. My calculator does not have a cube button. So the way that I'm going to do this on mine is I'm going to put in the 9.3. I'm going to hit the little button that looks like that. What's that called?
Caret.
I think it's called a caret. I don't know why. I think it's called that. And then a 3. So this means that we're raising 9.3 to the 3rd power. Your calculator is probably fancier than mine. It probably has a cube button. So I get that 9.3 cubed is something like 804, right, 0.357. That should have 2 significant digits. If you're unable to do the cube on your calculator, I can come help you in a few minutes. And then the final step is to take the square root of both sides, right, no problem. My calculator does have a square root button, so I'm in business. And I get like 28.36. 2 significant digits. So Saturn takes 28 years to go around the Sun once. 28 like Earth years. Right? So we can use Kepler's third law, right? If we know information about one planet, we can find a missing piece of information about another planet. Follow-up questions from anybody about this first example before we do a second one together? All right, let's do a second one, and then I'll have you do at least one on your own. All right, asteroid. We know what those things are? Some of you do. All right, so asteroids are kind of neat because most of them are located in just kind of one little region of space. All right, so here's the Sun. Who's first? Who's closest? Mercury. Right, and then who's next? Venus. And then who's next? Earth. Earth. And I'm not getting the distances right, but whatever. And then who's next?
Mars.
Mars. And then who's next? Jupiter. But we have some other junk in between. We have this like asteroid belt in between Mars and Jupiter. So that asteroid belt either used to be a planet and got like pulled apart and is now all that debris is kind of fanned out in that orbit in between Mars and Jupiter, or it actually was stuff that just never quite formed into a planet. But pretty much all the asteroids are located there. There are some exceptions, but this particular asteroid is in that region between Mars and Jupiter. All right, moral of the story, asteroids orbit around the sun, all right, which we need to know in order to use Kepler's third law. All right, so let's go quicker this time. I already drew my picture, right, done. I said I'm not actually going to overtly identify my variables if I'm trying to find orbital radii and periods, so I'm going to start right with Kepler's third law. What are we going to get to do for this one? Who's already looked ahead? It's exciting. Will, what are we going to have to do?
So you're gonna put the.
Oh, come on, 2
period
words. CR, 2 words. What am I excited about? CR. Oh, we don't see it yet. Very good. All right, so what do we know? We're going to make Vesta be object A, and we're going to make the Earth object B, because whenever possible we want our denominators to be 1. So this time we do know TA. It's 3.62998, very precise. And then that's in years, so the period of the Earth is also in years. And then what are we looking at? How much farther is Vesta from the Sun than the Earth? We're looking for this ratio. We don't have to find it in kilometers or miles or parsecs or whatever. We just want to know however far Earth is, how much further is Vesta. So we're looking for that ratio. All right, so let's see, what am I going to do? I can get rid of this denominator and just say 3.62998 squared equals the ratio I want to find cubed. What do we get to do? Come on, CR, what is it? Cubed root, come on, so exciting, we haven't done that yet. So 3.62998 squared. I have a square button, I can do that. I get 13.1767548 equals the ratio I'm looking for cubed. So we undo a square by doing a square root. We undo a cube by doing a cubed root. So I need to take the cubed root of both of these sides. My calculator does not have a cubed root button. All right, so let me show you what I did. So RA over RB equals the cubed root of this. The way I do it on my calculator is I put in the 13.1767548. I use that caret button again, but this time I raise it to the 1/3 power. Right? 1/3 power is the same thing as a cubed root. And I get something like wow, I should have 6 significant digits. Wow. So the ratio of how far Vesta is from the Sun to how far the Earth is from the Sun, 2.36194. There's no units there. There's no units. However far we are, Vesta is 2.36 times further away. All right? So those are 2 examples, right, where we're doing square roots for one, cube roots for the other. Let me go ahead and give you 2 problems that I'd like you to work on in your foursomes. The challenge problem is a good one, but I'm not going to wait for you guys to finish that. Once I see success from everybody on the first one, we'll move on and start talking about gravitation. We don't need to take this part.